yeah, I'd like to take up the discussion from the keynote this morning. So Benoit sort of presented some shocking news there. So 5 to 10% of software is developed in place, and then 90 to 95, then it's reused basically by open source or other third parties. So my goal here is to show you a little bit more concretely how we can sort of use that to achieve remote code execution, which is the very worst that can happen to your server, for instance. And maybe we talk about Derek as well a little bit later. So to do that, I'll focus on the web ecosystem. So I'm sure you're aware of the web architecture, but a very simple version of it is you have a bunch of clients. So you should never trust them. So some of them could be malicious here. And then on the back end, you have a bunch of technologies that you implement your servers. So one of the first use case we could look at is your server side is sort of implemented in memory-safe language. So, Derek's vulnerability won't apply here, but there are others. And our goal here is to really apply static and dynamic analysis to sort of identify vulnerabilities that lead to remote code execution. So code reuse, how does that work? Well, we use inheritance. So we import this code, and then we try to extend it to sort of our needs. So here is a classical example. If you take a course in object-oriented programming, you learn about design patterns. So one of those is what is called the I command, so the command design pattern. So what you basically do is you have some generic class, and then you have this method execute, and then you can sort of specialize it according to your needs. So for instance, if you are a client and you want to execute a backup on your database, then you just implement it in some way. So it doesn't matter the implementation here. And then you want to use this online, so you sort of expose it to your clients. So clients can call this action by specifying the type of command they want to execute. There's only one here, backup. And then some magic happens. So if you call this method with these two arguments, backup and then all, so you'd like to back up everything, then it goes through. So the database backup is carried out, and you're happy. So what happens here, of course, the whole point of code reuse is you could have other code that either you have implemented or maybe you don't even know it exists. It just gets loaded with your application. So remember Benoit's case, code is really bloated in this use case. So what happens if you have a different implementation? Now this case is to sort of execute commands on the operating system. And what this does is really, takes an argument and then starts a process to execute this command. Okay, so as a developer, you're not even aware of this case. So what you can do, well, now you sort of call the same function that is exposed to the client. So remember, clients can be malicious in this case. And then you pass a different argument. So in this case, you'll be executing operating system command with a calculator, which is the classical sort of case to show remote code execution. So this is bad, and you can already see here the attack space is sort of the set of these classes or types that are reachable basically through the code that you are reusing. So this is just to introduce you a bit to the problem, but I think we should look at something even cooler, which is when the backend is implemented in the most popular language on Earth, and the most horrible one, which is JavaScript. Okay? So we're in this case. So I'll just to walk you through basically through the steps of sort of doing static analysis and achieving remote code execution in real products. I'll give you some examples of that. OK, so how do we do code reuse here? So it's a little bit different. So here you have objects, not classes, and then you can extend them to your needs. So what's happening here is that I'm creating an object O1 is empty. There is nothing in there. OK? So when this is executed, what happens under the hood is that a runtime data structure is created and have this funny field called product. So this field is a pointer to a bunch of functions that you can reuse, basically. For instance, toString is just a function to print an object into a string. So far, so good. We want to reuse code here, so nothing happens. And now at runtime, you may want to sort of extend the properties of this object. So otherwise, it's quite boring to just use an empty object. So in this case, I declare a property x. And then, of course, I have to initialize it to 42, which is our favorite number today. So this is fine. So now I have an object which has one property and it has one value. So now things start getting more interesting when we declare an object which is completely unrelated for the first one. It's called O2, it's still empty. And now we try to access property X, which was sort of declared on the object O1, and try to read it, print it on the screen. Okay, so here is where the magic happens. So now what the runtime will do, it will say O2 is an empty object, so it doesn't have a property X. Aha, let's look at this prototype. And then in the prototype here, we'll find the value 42. So this sounds pretty cool in terms of usability, right? So inheritance, you can include all the code you like. So what's the security problem here? Let's take a look at that. Suppose we have a function. By the way, I'm showing you some code here. Don't worry, I'll explain it if you're not comfortable with code. So suppose we have some function entry point, and we have these 3 arguments that the attacker can control. He can set them to his wish. Okay? So what's happening here is that we're creating this empty object. So this is our running example here. And then we are trying to access some property of this object. So what happens if I instantiate this property to this sort of funny keyword prototype? Okay? So what happens is that I can now control the creation of new properties at my wish, basically. Okay? And then there are a bunch of other things here. So I'm accessing now. So having sort of achieved access to the prototype, I can start creating new properties, and I can assign values that I like. Okay? So in this case, what we do is we overwrite this function to string, and then we assign it a value that is unexpected by the system. So now, let's assume that we have the code down here. So we create an empty object and call toString, so completely benign code. Well, if the attacker manages to call this entry point with these 3 arguments that I told you before, this is denial of service, basically, attack. Now, denial of service is interesting, but kind of boring, so we want to achieve remote code execution here. Well, let's look at some helper function that you have in your system. So again, details are not important here. What's happening is that you specify the arguments, so some command you want to execute. And then you can give some options in terms of which shell you want to use. If you don't specify this option, then it will use the default bash shell, basically. Okay? And then it will execute the command. So yeah, so what we are using this function for here is this ls command, just to list sort of files in our system, and we're not providing any options. Okay? So what the system will do, it will take these arguments, it will see that shell is not defined, it's empty here, and then it will go for the bash, and then it will sort of show us the list of files in the directory. So now, what happens if we call this function entry point that I showed you before with slightly different arguments? So what we're doing now is we're going to this superclass through this product, and then we are actually defining this property shell to a calculator. Okay? And after that, we have this benign code as we had it before in our system. So what happens in this case? Well, we have executed this entry point, so now we have this new property shell initialized to the calculator. So we go through our function again, and now when we execute the command, now we do have an option. Well, it will try to access shell. It will say, this is an empty object, so shell doesn't exist. Let's look at this prototype. Okay? And then in this case, it will read calculator, and then you get remote code execution. Okay? So there are 2 steps here. So first is this funny pattern that I showed you to pollute the prototype, and the second is to find these gadgets that can do damage, basically. So yeah. Okay, so our goal with this paper is exactly to achieve this. So to automate through static analysis, how do we identify these prototype pollution, so these patterns? How do we identify gadgets, so things that sort of make the damage in the system by executing code? And then how do we put it all together? Okay? So first step, how do we do this? And we want to do it scalably, so to sort of basically analyze real code, real application. OK, so we use a technique called taint analysis, which some of you may be exposed to. So what we do is that if there is some argument that the attacker has access to, then we put a label. We say, this is untrusted. And then we start sort of propagating those labels and see if they sort of achieve the pattern that I showed you before. Okay? So again, code not important here. So suppose the attacker can control this diff. So then diff is controlled by the attacker. Well, you access some field path. If you control the object, you control the property. You do some operation. You assign it to some variable. And then at this point, you get the first argument here, which is the control of the product. So now you're accessing an object with this property that is controlled by the attacker. So you achieved your first step here. So now that we have this control of product, then we want to assign properties at wish, okay, of the attacker, and also assign values at wish here. So we go on. So object now has control of the product. Again here, now we have the pattern that we like. Okay? So now if we can control last prop and this diff.value, then we're done. So we have the thing we're after here. Well, what do we do? So we continue with the data flow analysis. So we control diff, we control path, we control the pop. So then we control the first argument, and the same for this one. Okay? So how do we do that? Well, there is a very cool static analysis tool. So I recommend you to take a look if you haven't already. It's called CodeQL. So basically here, the idea is that you take some code base, and then you represent code as data in the database. And then if you want to implement analysis like this taint tracking that I mentioned, then what you do here is really build queries, like querying a database, and those would correspond to your analysis. So the example I showed in the beginning with this multi-label taint tracking, we have developed it by basically extending CodeQL to sort of handle this kind of use case. Okay? So step one, we have this system that takes a code base and then will identify potential prototype pollution. So now we're left with step two, which is detecting these gadgets that we can do real damage. So what we want here is we want to do the analysis at the backbone of the server, Node.js-based server execution. Because if we find gadgets there, since all the applications that are built on top of Node.js are relying on Node.js in a sense, then we get what we call universal gadgets. Okay? So that would be very dangerous. So how do we do that? Well, here we're lucky. So remember what we need to do. We need to identify these properties that are undefined. They're not initialized. So then we can use the first step to sort of initialize that at wish, in a sense. That's our goal here. So first step is we look at these APIs. Node.js, is a real-world system. It's well-tested. So we just use the test suite, basically, to identify some properties that could be sensitive. Okay? So in this first run, we get a bunch here, like shell, or env, and so on. So now we say, OK, so this we can control through prototype pollution. So now can we find some things there that will do the real damage? For instance, execute code into the system. So that's the next step. Again, what do we do? This sort of taint analysis. So again, don't try to understand this code. I don't either here. But what's important is there is this ops.env. So env is being read, but it's not initialized. So we do some data flow analysis here, and it turns out that we are calling some function that spawns a process. Again, it's static analysis. There is no guarantee, but this could be a viable execution. And it turns out that this data flow occurs in this spawn function, which is the actual function to spawn a process in the system. Okay? So we do this analysis, and then we find out that, well, this property env, which is setting environment variables, and shell, those can reach the spawn function. Okay? So now that we have this, then we can build what is called a universal gadget. Because if we're able to pollute properties like this at wish, then we can execute basically processes in the system, so we get remote code execution. OK? So let's take a look at those. So I have my application here. It's very simple code. I just call a library I want to reuse. It's called child process. And then I call this spawn function, which is just listing the list of files in my directory. There is no control of the attacker at all here. If you look at the arguments, they're just constants. I'm just listing the files in the directory. Okay? So now what happens if you manage to control these three properties that I showed you before? Well, what you can do is you can set the shell to node, so executing the process, and then you can modify the environment in such a way that you get something called the remote shell, basically. So again, if you manage to do prototype pollution, then you get this gadget. So this is nice. Well, this is not nice. This is horrible, actually. But yeah. Gadget 2 is exactly the same. So what we find there is that all the main commands in Node.js, like spawn, spawn sync, and so on and so forth, they're vulnerable to this kind of attack. Okay? One more gadget. So I have this code that is just sort of requiring the library called bytes. This is just parsing basically strings of bytes into doing some formatting. So nothing happens here. Well, it turns out that if I manage to pollute another property that we found before, this is called main. So this is basically specifying where the execution starts. So if a library doesn't initialize the beginning of the execution, you can just point it to some malicious file in the system, and then there you go. Then you get them executed. So now you would say here, OK, this is kind of cheating, right? Because if I have malicious files in the system, then I can just do malicious things directly, right? I agree with that. But once we have these two gadgets, then we can, if you like cocktails, then we can start putting them together. So if the first gadget was rum and the second was Coke, then we do Cuba Libre now. Okay? So let's try to do that. So let's see what's happening here. So I have some file that comes with the system itself. It doesn't really matter. It's called changelog.js. So all I know about this file is that it will always get executed, and it calls this spawn function. Okay? So now all I need to do is just point my main to a file that exists in the system. That file will execute spawn, and then I combine it with the first gadget. Okay? So sort of it becomes easier for the attacker here too. Again, another file in the system is this npm.js, which calls the node process. Again, details don't really matter here, but I can achieve remote code execution either with sort of less effort here. Okay. And now these are proof of concepts I show you, right? So you wonder, yeah, but does this really work in real systems, right? How do you put these things together and so on? So I'll give you sort of a flavor of that. So how do we identify these entry points that are controlled by the attacker? Then remember, we have to do two steps: prototype pollution, and then find the gadget. So how do you do that? Well, you just look at real applications, right? So what we did is we crawled GitHub for server-side projects, and we took the most popular ones together with this npm CLI, which is the command interface for installing packages, basically, what Benoit used this morning. OK, so here are a bunch of those. So we run these tools. And then what we find here is what you see in this column, total. OK? So surprisingly, given that we're aiming for remote code execution, there are not many cases. So static analysis are known for many false positives. It doesn't happen here, and one reason could be the shape of these prototype pollution patterns that we're looking after. OK, and then we do some classification here. So what we find, and this is sort of manual work, is that for one tool called parserver, then this was a year ago, we found only one RCE. And we found 2 for the npm CLI. So these numbers have increased now because what we call suspicion here, so now it becomes more an art than a science. You have to sort of scrutinize these paths and then see if you could exploit them. So what we have now is many vulnerabilities, so remote code execution on high-profile systems like parserver, Rocket Chat, npm CLI. We got some on Kibana as well recently, so this is to be continued. But let me give you a flavor of, so this is a list of vulnerabilities. So if you're a PhD student, want to work on this stuff, you can top up your salary a little bit by participating to these bug bounties, which, by the way, is the topic of the panel later. OK, just to give you an idea, right? So npm CLI is what you'd use to install packages or publish them in the package repository. So they have some sort of threat model. So they tell you if you manage to achieve script execution upon a package install, it can be malicious, but it has this flag, -- ignore scripts, then you get code execution in the system. If you bypass this, then you made it. So what's the model here? So the attacker crafts a malicious package and then puts it to the npm repository. So it just goes like this. And now as a developer, you do npm install, but then you're careful. So you use this -- ignore scripts. So it should work, but actually it doesn't. So how does it work? So this is kind of the payload here. Again, please do not understand it, but let me show you the function that I used as motivating example before. So what's happening here is that if the attacker controls the diff in some GitHub repo, basically, so by executing this payload, then you can inject proto here, then you can change the environment to this last property, and then set the git command to the calculator. Okay? What is the gadget? Well, is sort of a little bit similar to the spawn example that I gave before. So again, details are not important here. What is important is that the code that we polluted at this step will now be initializing this opt.env that is uninitialized. So the developer, has just configured some GitHub environment. It doesn't really matter here, so it's all benign. But due to prototype pollution, well, then we'll achieve remote code execution here. And this is just a little sort of example that this works. See? Yeah, and you achieve calculate. OK, so just to summarize, code reuse attacks, I think they can have real impact, especially in the context of web applications, and we should take them very seriously. We also learned that at least for these types of vulnerabilities, doing large-scale static analysis, it helps to actually identify these vulnerabilities. We have found many of those, and this is even to be continued. So with that, thank you very much. I'll be happy to take some questions.
Wonderful. Thank you.
Thank you.
Questions? There's one over there.
So, thank you. Prototype poisoning is quite a specific JavaScript concept, I guess.
Yeah.
So, what in this is specific to prototype poisoning in JavaScript, and what would be a more general attack methods for other type of inheritance in other programming languages and so on? Is this because JavaScript is bad, or is it a more general problem?
So yeah, it's bad and it's hard to fix because in a way it's a sort of prototype inheritance. Is used as a feature, but then on the other hand, you can sort of abuse it. What makes it more dangerous compared to, say, object injection vulnerabilities like insecure deserialization, what I tried to explain earlier, is that basically the attack space is huge because in a way or another, for managed language, you have the type that sort of constrains the set of possibilities you have. But with prototype pollution, as you saw, it's just huge space. There are no good solution at the moment, unfortunately. I know Google is working on sort of proposing a new standard where you can modify the V8 engine to sort of automatically, access this product keyword through well-defined APIs. That could be something in the right direction.
Thank you. Yeah, great presentation. I was curious, as a defender, since you build this on top of CodeQL, can we benefit from those, I guess, rules or detections, or do you have other pointers we could benefit from?
What's in there, you mean, in CodeQL?
Yeah, no. What you said you build the detection, or on top of CodeQL.
Yeah.
And CodeQL is pretty much an engine and some rules, right?
Yes.
And I was curious if, as defenders, we can use those rules to kind of find out about potential.
Absolutely. So actually, I think I had, I'll show you this slide here. So what you see in these baseline queries is what already exists in CodeQL. So what we do in this work is we sort of extend it significantly because you need this special language feature. So we want to cover as much as possible on Node.js. And the other part is this data flow, this multi-label taint tracking that I mentioned. So if you want to search for prototype pollution in your code base, I would suggest you look at our tool. I think it's a little bit better.
Okay. Thank you again.
Thank you.
Musard.